All right, so I'm sorry I can't be here with you guys today. So hopefully this video will help. I encourage you guys to watch this at your own pace. If you need to pause the video at any point and try to figure out what was just said or what's going on, feel free. Rewatch the video as much as you need, whatever you need to do, and hopefully this will help. So today we're doing section 2.7, inverse functions. So what are inverse functions? Well, you probably already have an idea of what inverse functions are. If I asked you what the inverse of addition is, most of you would probably say subtraction, which is absolutely right, because they undo each other. The inverse of multiplication is division, because they undo each other. And that's exactly what inverse functions do. They undo each other. So let's see, well, what does that mean, they undo each other? Well, let's say that we have some function, and I'm going to call that function f, and we have an input of f. So we take some input value, we put it into f, and we get an output of f. Well, if we have an inverse function, so let's say we have the inverse of f, I should be able to take the output of f. It now becomes the input of the inverse of f. I put it into the function, and I get some output of the inverse of f. I'm right back where I started. It undid it. So I take an input, put it into f, I get an output. I take that output, put it back into the inverse, and I wind up right back where I started from. And that's all it is. Now, God, that's kind of a mouthful though. Inverse of f, inverse of f. I didn't even finish writing f here because I apparently got tired of writing f's. So, but we have a notation for that. So I'm going to say the notation for the inverse of f of x. It looks like this. It looks like an exponent of -1, and I hear people read it all the time, f to the -1 of x. That actually is nonsense. That doesn't make any sense, f to the -1 of x. Instead, you literally read it as the inverse of f of x. So instead of saying up above, instead of saying the inverse of f, instead of saying the inverse of f, instead of saying the inverse of f, I could have just said this notation right here. But again, it means the same thing. I start with some input of f, put it in the function, I get an output of f. But if I have an inverse function, that output can become the input for the inverse, and I wind up right where I started from. And that's what inverse functions are. So let's see a formal definition of inverse functions. So this is a more formal definition. Definition of inverse functions. If f of x and g of x are inverses of each other, then, and here's what it looks like. You can take some value of x, you can put it into one function, and you get an output, and you can take that and put it into the other function, and you should wind up right back where you started at x. And it shouldn't matter which function you start with. I can take x and put it into f, take that output value, and put it into g. No matter which way I do it, I should get x. And that's the definition of inverse functions. So let's take a look at what this means a little bit. And how do we verify that two functions are inverses? I'm going to leave that there. So example, verify that f of x, where's my example? F of x equals 5 over x minus 2, and g of x equals 5 over x plus 2 are inverses of each other. Now let's take a look. So just like the definition shows, I should be able to do f of g of x or g of f of x. Either way I get x. I have to show that both ways work. So let's find f of g of x. Well, remember, this notation means we're going to take g of x and put it into f. So here's f, 5 over x minus 2, but instead of writing x, I'm going to write what g of x equals. And then I still have the minus 2. So this part right here was g of x. Well, the 2 minus 2 cancels out, so I just have 5 over x. But that's 5 times x over 5, which is just x. Oh, sweet. Well, that worked. But that's not enough. I have to show that it works the other way. So I have to go g of f of x, and let's figure out what that equals. So now I'm going to put f into g. So g says 5 over x, but instead of x, I'm going to write what f is, and it's plus 2. So this right here was f of x. Well, again, I'm dividing by a fraction, so I'm going to multiply by the reciprocal, but then the 5s would cancel, and then the 2s would cancel, whoops, and I got x. Yay! And this is where most people will stop, and you're going to lose a point on the test if you do this, because there's one final thing you need to say. You're basically proving. When we want to verify something's true, we got to prove that it's true. And in math, proofs are very formal. Actually, let me leave that there. You need to state this definition somewhere in your proof. So I'm going to do that right now. I have said that f of x, whoops, I have not said that. I have said that f of g of x is equal to g of f of x. I've just shown above that both of these are equal to x. So therefore, if you've never seen these three little dots in math mean the word therefore. So therefore, f of x and g of x are inverses of each other. And you're done. That's it. So, to use the formal definition and show that they're inverses of each other, this is what you got to do. All right. Excuse me. How do you actually find inverses, though? So finding inverse. Let's see. Finding inverses. Let's do it graphically first. So graphically is not so bad. Like actually finding inverses anyway. I'm going to go back up here for a second. Remember this thing right here? This little circle, how the input of f becomes the output of the inverse of f, and that the output of f becomes the input of the inverse of f. That's kind of important here. We have f of x. We have the inverse of f of x. They both have their own domain and range. But the input of one becomes the output of the other. And then likewise, the output of one becomes the input of the other. The domain and range basically switch roles. I'm going to go back up here again. The input becomes the output becomes the input. That's exactly what we're showing down there. So if the domain becomes the range and the range becomes the domain, and the x values are the domain and the range is the y values, if the domain becomes the range, it's like the x's become the y's and the y's become the x's. You switch x and y. To find an inverse, switch x and y. Like, literally, that's it. To find an inverse, that's all you got to do. So let's look at a couple examples graphically. We'll do an example algebraically, and then we'll be done. So graphically, let's just say we have a relation. I'm going to say relation because it may or may not actually pass a vertical line test. It may not be a function, but this still works. And then we have the inverse of relation A. Well, if I tell you these points, 1, 2, 3, 5, and 6, -8 are all relation A, then for the inverse of relation A, you literally switch x and y. Instead of the point 1, 2, you now have the point 2, 1. Instead of the point 3, 5, you now have the point 5, 3. Instead of the point 6, -8, you now have a -8, 6. Like, that's literally all you do. It can't get much easier than that. If I were to graph these, hopefully I'll have enough room. Ooh, I think I'm just going to make it. Okay. I'm going to graph these in this pink color. So we got the point 1, 2, the point 1, 2, 3, 1, 2, 3, 4, 5, and then the point 6, -8. Might move this over just a little bit here. So 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8. Whoop. So here's all our points. If I were to graph these guys in this teal color, then we have the point 2, 1, the point 1, 2, 3, 4, 5, 1, 2, 3, and the point 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6. And there we go. Now, why did I do that? Well, take a look at that picture. It's only a few points, so it may not be totally obvious. But do you see any symmetry in this picture? We do. We have nice symmetry right here about this line. If I folded the screen along that dotted line, you'll see the red points line up with the teal points. And hopefully you guys recognize this line as y equals x. So it turns out that graphs of a function and its inverse are reflections about the line y equals x. So when you're actually doing finding inverses graphically, and it just kind of depends on the person. Some people think numbers and algebra, but stronger than geometry. It depends how much of a visual person you are. But to find inverses graphically, you can either think about switching the x and the y coordinates, or you can think about reflecting about the line y equals x. Either way, you're going to get an inverse function, or an inverse, I should say. Again, it may not actually pass the vertical line test. It may not be a function, but we can still talk about inverses. So they are reflections about the line y equals x. Now I want to take a look at a couple that we should be pretty familiar with. So let's look at this example. If we were to look at y equals x cubed, actually let me use function notation. If we have f of x equals x cubed, we know the inverse of cubed, something that undoes cubing, is cube root. Let me actually use this color. So the inverse of f of x is the cube root of x. Now let's actually take a look at the points and their graphs, and we'll see switching x and y works, and also reflecting about the line y equals x, that works. I'm going to go ahead, put a set of axes here. Sorry, my line's not super straight. All right, so let's first look at this guy right here. So remember the points, you guys should be familiar with that parent function. 0 cubed is 0, 1 cubed is 1, and then 2 cubed is 8. So 1, 1, 2, 8. These are on the graph. Also, negative 1, negative 1, and 1, 2, 3, whoops. 1, 2, 3, 4, 5, 6, 7, 8. Negative 2, negative 8 is also on there. And there's what the graph looks like. Okay, so now I'm going to go ahead and graph its inverse. And again, based on what we did with our parent functions, these points should be familiar to you. The cube root of 0 is 0. The cube root of 1 is 1. And then 1, 2, 3, 4, 5, 6, 7, 8. The cube root of 8 is 2. So that point is also on there. And then likewise, the cube root of negative 1 is negative 1. And 1, 2, 3, 4, 5, 6, 7, 8. The cube root of negative 8 is negative 2. And, oh, missed a little bit. Oh, I don't like the way that looks. Let me graph that again. So now we have that one. I'm still not hitting it. There we go. That's better. So then we have the cube root graph. And notice we could just graph them by switching x and y. But it's also the reflections about the line, if I can get it. Oh my goodness. Y equals x. Now I want to do this with the square and the square root function, and some of you guys might already be seeing what I'm getting at here, and maybe asking this question to yourself. But let's look at f of x equals x squared versus the inverse of f is the square root of x. They undo each other. So Let me go ahead, get these lines here. And we know the point 0, 0, 1, 1, 2, 4, and 3, 9. And then these corresponding points on the other side. These are all part of y equals x squared. And if I were to switch x and y, this point right here, which was at 3, 9, it's going to go to 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3. It's at 9, 3. And this point right here, which was at 2, 4, it's going to go to 4, 2. One, 1 is going to stay 1, 1, 0, 0. But then this point right here at negative 1, 1 is now going to be at 1, negative 1. And this point right here at negative 2, 4 is going to go to 1, 2, 3, 4, negative 2. And then likewise, we have the point 3, 9, or negative 3, 9, which is going to go to 9, negative 3. And we have this new graph here. And so we have its inverse. Or wait a minute. This square root function, if you go back to what we did with parent functions a few sections ago, the graph of y equals the square root of x, it doesn't have this bottom part to it. What the heck? Well, notice also right now with what I've got, that green graph is not a function. It fails the vertical line test. We want functions, so we're going to get rid of this part, which isn't even part of the square root graph anyway, but now we don't really have reflections about the line y equals x. We have this part of the red parabola that doesn't have a corresponding part on its inverse. In order to fix this problem, what you'll often see being done when we're dealing with inverses, we restrict the domain so that way we have true inverses of each other. If I say x is greater than or equal to 0, it gets rid of all of this stuff where the x values are negative. And now we're left with a good-looking graph. It actually, the two graphs really are reflections about the line y equals x. We have inverses. The inverse is a function. All is well. All is happy in the world. So it's not a big deal. But that's why sometimes you'll see we put these restrictions. Like f is just saying x squared. We can square any value of x. Why would we do this? Why would we say x is greater than or equal to 0 when we can take any number and square it? Well, we're doing that so that its inverse is actually a function. So then speaking of that, remember we had the vertical line test. And the vertical line test was used to see, it checks if a graph is a function. Well, we also have something called the horizontal line test. And the horizontal line test checks if the inverse of a graph is a function. And the cool thing about this is it checks without drawing the inverse. So for example, I'm just going to do a loose graph of this. That parabola that we did, this parabola passes the vertical line test. I can draw a vertical line anywhere. It's not going to cross more than one. So the graph is a function, but it fails the horizontal line test, and that means its inverse would not have been a function. And so that's a way you can check without actually drawing the inverse. So it gives me one definition, one more definition here, and then we just have one more example and we'll be done. So a one-to-one function, you can think of this one in two ways, but it means the same thing. You can either think of it as a function that passes both the vertical and horizontal line tests, or you could think of it as a function excuse me, whose inverse is also a function. Ta-da! And so, for instance, the cubic function, I'm just going to scroll back up to this example. This original cubic function, notice that would pass both the horizontal and vertical line test, and sure enough, its inverse is a function. It worked. It's a one-to-one function. So that's all a one-to-one function is. You'll hear that term used. All right, last thing. How do we actually find an inverse algebraically? Finding inverses algebraically. All right, I'm going to do part A. Let's say we had f of x equals 5 minus 3x over 2. Well, remember how with graphs, where did I put it? Right here. To find an inverse, you switch x and y. Well, guess what? To find an inverse, you switch x and y. That's literally it. Where's my example? Sorry. We don't have a y right now, so that's our first thing. We need a y. So we're going to say y equals f of x. And so now we have y equals 5 minus 3x over 2. All right, so now we have it. So we have an x and a y. We can actually find the inverse. Now, as soon as you find the inverse, you should label it. So I'm going to write the word inverse here. And we're going to literally switch x and y. Boom, found the inverse. Now, unfortunately, I can't do that. I can't just leave it like that because I need to be able to use this notation. I need to use that -1 notation. So I have to solve for y. Not a big deal on this one. I'm going to multiply both sides by 2. I'm going to subtract 5 from both sides. Just going to rewrite it up here. To get the y by itself, I got to divide by -3. I'm going to go ahead and put the y on this side of the equal sign. I'm also going to reverse the order just because I like to lead with a positive. So a -5 divided by -3 is going to be positive 5 over 3. And a positive 2x divided by -3 is going to be a -2x over 3. So now I've solved for y. So that means its inverse, the inverse of f of x is 5 minus 2x over 3. Dun, dun, dun. And that's literally it. To find inverses algebraically, you switch x and y, but then you got to solve for y. There you go. All right, so that was part A. That must mean there's a part B, and there is. Let's just do one more example. If you want, I would encourage you guys to, it's going to have just a little trick in it, but I would encourage you guys to pause a video, try it on your own, and then we'll take a look together. All right, so go ahead and pause the video right now and give it a shot. All right, I'm assuming that you paused the video. I'm going to go ahead and do it, and I'm just going to do it kind of quick, but again, before I switch x and y, I need a y, so I'm going to let y equals f of x. So y equals 2 minus 3x over x plus 1. Now I switch x and y to find the inverse. So I label it, and I have x equals 2 minus 3y over y plus 1. Yay, I found the inverse. Here I got a problem. How am I going to get the y by itself when the y is in two places? Somehow I got to find a way to get the y in one place. I got to find a way to combine them. And right now I can't do that. Well, let's see here. I got a denominator. We'll multiply both sides by the denominator. Now here's where the trick is. When the y appears in more than one place like this, we can go ahead and collect all the terms with a y, and we'll be able to factor it out. You'll see what I mean. Except before I do that, right now this y is trapped inside the parentheses. I need to get him out of there, so I'm going to go ahead and distribute the x. I got xy plus x equals 2 minus 3y. Now I'm going to get the y's on one side and everything without the y on the other. So I have xy over here, so I'm going to add 3y to put it on the left side of the equals. And then I'm going to subtract the x to put it on the right side of the equals. So now I got everything with the y on one side, everything without the y on the other side. Now that the y's are together, I can factor out the y. And then finally, to get the y by itself, I can just divide. So the key was getting the y's on one side together so you could factor them out. And then I'm just going to use my inverse of f of x notation to write my final answer. And there we go. So there's finding inverses in a nutshell. Let's just do a quick recap. So I'm going to scroll back to the beginning. All right, so remember inverse functions undo each other. The input of one becomes the output of the other, and then vice versa. We have our composition definition of inverse functions. F of g of x equals g of f of x equals x. So to verify that two things are inverses, you have to check both ways. And don't forget to make this final statement in your proof. Otherwise, you will not get full credit. In general, to find inverses, all you have to do is switch x and y, because the domain of one becomes the range of the other. So the x values of one become the y values of the other, and vice versa. So you literally just switch x and y. That means that inverses and their graphs are reflections about the line y equals x. And we have the vertical line test, which checks if a graph is a function. Horizontal line tests, they check if the inverse would be a function. One-to-one is where the function has an inverse that's also a function. And then finally, finding inverses algebraically, you switch x and y and solve for y. So there it is in a nutshell. Hopefully this helps. So now you guys can use the rest of time to work on your homework together. I encourage you guys to work together on this. I expect that you are working. If you happen to finish early, you may work on some other class, but otherwise just keep working on this, and then I will see you guys when I come back on Thursday. All right, have fun.